Alright guys, welcome back, and in this video I'm just going to go over a little mini project or a hackathon project that I was a part of this past weekend for DubHacks. We ended up doing a haptic wristband for visually impaired individuals, combined with the camera system with the visual language module, which I'll get to later, but we ended up winning Best Freshman Project and Best Use of D11 Labs API. I was particularly responsible for the hardware, so I'm going to get through what I kind of worked on over the past weekend. So let's get into it. Yeah, so I just gonna go through the high-level architecture of just what the project does technically for this weekend's project. So the idea was a directional haptic feedback, which was given via a couple of vision models. We had a VLM and we had a segmentation model on a camera. So essentially, we'd have a camera Intel RealSense camera that passes its video stream up to the Raspberry Pi, which passes to the AWS cloud, where that's where the computer stores, because it's obviously a very heavy vision model, so we have it on the AWS cloud. The AWS cloud returns back an array of, okay, I want to buzz, say there's an obstacle right in front of me. I want to buzz the front haptic at 60% based on how close the object is. And it passes that matrix of how many, with the percent strengths of each of these haptic buzzers to the Raspberry Pi again. The Raspberry Pi is essentially our edge device, and that Raspberry Pi passes it to the haptic wristband, which I designed, and I'll show more in depth in this video, via BLE, which is Bluetooth Low Energy. So that's essentially the entire system, which is essentially a directional haptic feedback system for visually impaired people. So I'll get into the mechanical and electrical design considerations. I think going into this, the most important thing for us was time, or for me, it was time, was 24 hours. We had to build, program, and eventually present this project. So time was a huge constraint, especially for hardware projects and hackathons. So time was definitely one of our biggest design considerations, but we also had, for mechanical especially, thermal vibration damping. Very important, especially for haptic devices. I would say vibration dampening is very important because if you have, say, we had 3 haptic buzzers on our haptic wristband, but say you have an X amount of haptic wristband buzzers, you want to be able to differentiate from where the haptic buzzer is coming from. Is it coming from the left? Is it coming from the right? Because essentially that's the entire premise of what the project is going to do. So if there's a lot of vibration bleed, if it feels like it's just the entire ring is just vibrating, and you can't really pinpoint which haptic buzzer is buzzing, that's gonna be a real big problem. So that was probably one of the biggest considerations for mechanical, along with the material selection and integrity, just general considerations there, and then weight. We obviously don't want it to be a very heavy component. We want it to be almost seamless. Obviously, given it's only 24 hours and it's just a prototype, but at the end of the day, we do want it to be something that people can wear. For electrical, it was the size of the components again. You want to make sure it's small and can fit on your wrist or your arm, in the case that we actually submitted. And then one of the bigger things was we don't have a firmware person on our team, so I wanted to get much hardware as possible, and you'll see in the technical specs here that I can compensate for that by having less firmware written for if I can provide hardware that makes the firmware easier to write. And that came in the form of the driver boards, which I'll explain about later. And then, since this was my first mechatronics project, obviously I just put down ensuring compatibility through components. It's my first time sourcing electronics and seeing how different parts fit together, so definitely one of the bigger parts of the components. So let's go over to the electronics design and diagram. So the wearable itself, this is the haptic wristband. The wearable itself is powered by an Adafruit Feather NRF 52840 Sense microcontroller, which serves as the BLE receiver and the haptic controller. So this is mounted on the wearable itself. It's compact size, it's the onboard sensors, and it has an IMU on there, and the low power design make it really ideal for these wearable applications. So that's the Adafruit Feather Sense, and then because the the driver boards. These are DRV2605L driver boards from Texas Instruments. Because those driver boards all share the same fixed I2C address, so that's the I2C address of those driver boards are 0x5A. I need to use a I2C multiplexer or a MUX, which is included to like manage the communication between multiple driver boards. Each of the four driver boards controls one haptic buzzer, and they define the driver boards are there. Again, you could write the firmware for this without the driver boards, but it's really hard. And the driver boards also, I mean, it's not really hard, but we would have the experience for it. And also, the driver boards make it really easy to define the waveform intensity of the vibration feedback. And they offer like a library of pre-built haptic effects and support PWM-based control for custom patterns. And the driver boards seem like the obvious choice, especially for hackathon, where we only had 24 hours and we need to get something on presentation day. And then I'll not include in this diagram is the power. The power is provided by a 3.7 volt, 350 milliamp lithium-ion LiPo battery. It's a compact size and it powers the entire wearable itself. The rest of the system is the Pi and the camera, and that is powered by a battery bank that you can put in a pocket just for the hackathon's sake. And I'll show you more in the demo video. Go to the mechanical design over here. So the main choice there was, again, vibration dampening. And I had really two options here. Was between printing and PLA, which would take 2 hours for this entire CAD design to be printed. So this is a CAD design. Very simple, very rudimentary. I believe it was CAD'd within 30 minutes. Because we need to get on the print bed as much fast as possible. This PLA design takes only 2 hours to print, but if I was to use active foaming TPU, which is a special type of TPU which has incredibly good structural mechanics for like the strongest ones I've seen from TPU, I will have videos out on research. I'm writing a research paper on this material and lattice structures on that, and another product design that I did over the summer. I'll have those out soon. But essentially, for vibration dampening, plastics like PLA, and you can see this literature right over here by Kitagawa et al. About how PLA is it's far worse at vibration dampening because the molecules are much more closer together, so the vibration waves get like passed a lot easier. So it's a lot more effective to use active foaming TPU, which is a type of foam. It's CO2 bubbles inside, so it is foamed. So I did end up I wanted to do active foaming TPU. Unfortunately, the print took 12 hours because we had to print slow. So we weren't able to get it for the DubHacks submission date, but I do have the module in my hand, and I'll probably be posting a picture and link below. But that was the main mechanical constraints apart from the obvious pretty CAD design. But yeah, that was essentially a project, and we have a little demo video just so you can see the entire system. Let's see here. Yeah, so I'll pause it here. Let's see. Essentially, the wearable itself is right here. I'm blindfolded, and then we have the camera, and the Pi is in my pocket, and the battery bank that powers the Pi is in the other pocket. So that's the whole system. Obviously, just very rudimentary for the hackathon itself, but yeah, that was our hackathon project. Thank you for watching. I'll catch you in the next one.